Here we go. I'm very excited today to be talking again with one of the smartest guys in FPV, Ryan Harrell. Ryan did some interviews with me a little while ago where we talked about motor KV and motor theory. And Ryan, that's something you really excel at because of your experience with your website, miniquadtestbench, where you test motors in so much detail. And you reached out to me after I did my video with the 6S 2700 kV, quote unquote, 160 mile an hour quadcopter. And I say quote unquote because it's not legal to go over 100 miles an hour. And you said, I want to talk about the problems, because a surprising number of people were like, yeah, that sounds like a good idea. Let's do that. And then they were reaching out to me and saying, we're having desyncs, where quad is falling out of the air when I go above 70% throttle. And I was like, yeah, of course it is. What are you nuts? The 6S 2700 kV. What did you expect to happen? I don't know how anybody. And you said, let me tell you all about it. So Ryan Harrell, welcome to the show.
Thanks. It's always good to come on and talk with you.
Indeed. It's been too long, actually. So how do you, well, let's start with this question. When you have a 2700 kV motor on a 6S battery, why is that a problem?
Sure. Well, there's a couple of reasons. If you think about it, your RPMs are going to be a lot higher than what they would be on another setup. So higher RPMs mean that the ESC has less time to detect those zero crossings. Means that there's a lot more happening a lot more quickly in the ESC. Also, you end up with transition spikes in terms of current changes in current delta. That's going to be a lot higher than what you get on some of these smaller lower kV motors, simply because, remember, kV is proportional to the torque constant. Torque constant says how much current does it cost me to make torque. So when you're doing very rapid changes in RPMs, that's requesting a lot of torque, which means that it's going to create a lot of current moving through the coils in the motor. So all of those things combined together, mean that you're going to have higher noise levels in the ESCs, which again complicates detecting that point where the magnet passes the coil at the peak point, where what we call a zero crossing.
Right.
That zero crossing. If it can't detect that zero crossing accurately, then it's not going to know when to fire the next phase. And it can do that a couple of times and just kind of guess and be okay.
Right.
But if it can't detect the zero crossing after a certain number of times, the ESC will just shut down.
The analogy that sort of made this click for me is, think about like the merry-go-round in the playground, and your kid's on the merry-go-round, and you grab the bar and you give it a whip. And then as the next bar approaches, you grab that bar and you give it a whip. But if you were to just stick your arm out, the bar would crash into your arm and you'd break your arm, and that's a desync. As the motor spins, the magnet rotates past the poles, and the ESC needs to drive current through the stator such that it sort of pulls and pushes at the exact right moment. And what you said really, I didn't really think about this, but it's obvious when you say it. The faster the motor's spinning, the less time there is to detect the approaching zero crossing and then like make all the things happen that need to happen. The current to rise and the magnetic field and so forth.
We're talking about these things are still processing, really fast compared to what we think of in terms of human terms. So yeah. even then, it's generally, the timing isn't as big an issue. But when you start talking about dead times and the window between the dead time and when it can actually fire, it's just everything gets more compressed, and there's just more chances of something going wrong. Particularly given the fact that a lot of these ESCs, I'm not dogging on manufacturing, but we're hobby grade manufacturing, right? We're not massive.
Right.
So when we're talking about the type of variation that they have in the components that are being used, we have a fairly large window of variation. So if the dead time is slightly off based on, they have a manufacturing specification that's saying the dead time should be within this window based on these parts. But if the parts are slightly different and that dead time gets a little bit off, you can end up with things like shoot through becoming more of a problem. that's not as much a desync problem, but if the dead time isn't optimized, you end up with more noise coming through the ESC, which can impact how you read the zero crossing.
What is dead time? For people who don't know, what's dead time in an ESC?
So dead time has to do with the amount of delay that it puts between when one half of the phase goes off and the other one comes on. So when you're dealing with it's an H bridge, essentially, if you're familiar with electronics at all, where you have a high side and a low side FET. So the dead time has to do with how much time it gives for the current to dissipate between turning on turning off the high side and turning on the low side, or vice versa. Because if you turn them both on at the same time, you effectively get a short circuit that allows current to just then
you fry your motor,
which ends up increasing heat and causing all kinds of problems. I remember back in the day, I had some ESCs where the dead time was incorrect, and they would heat up like blisteringly hot within a few seconds.
I guess it would fry the ESC because you'd have a short circuit inside the ESC.
Correct.
You want a short circuit through the motor because that's what drives the motor.
Right. Not between high side and low side phases in the ESC.
Yeah. So the dead time is important because the FETs, which are just basically tiny little electrical switches that switch voltage or current on and off, the FETs don't turn on and off instantaneously, right? That's why you need the dead time. Because there's going to be some window where the FET is kind of like a little open and a little closed, and you don't want what's called shoot through. Is that what the name is for that short circuit? Is shoot through?
Correct. So yeah, it's and again, it has to do with how the gate line is designed, what capacitance is on the gate line. There's all kinds of just small things about how the ESC is designed that can change what the ideal dead time for that ESC is. Obviously, we want the shortest possible dead time that we can get to allow the fastest possible switching rate, but you don't want to cut it so close that you're causing problems. So
right.
The manufacturers are supposed to provide those dead times to the firmware developers.
Right.
So, obviously, there's been a couple of situations that we run across recently where the dead time that they were providing was not necessarily accurate, or they would make a modified version of the firmware themselves, and the dead time label in the firmware was one thing, but then they went into the code and hard coded a change to it that made it look like it was something else. So what happened is that when people upgraded the firmware, they fried the ESC. Right, essentially, because the manufacturer was screwing with stuff behind.
So we've got a situation here where the manufacturer designs the ESC, and it sounds like they design it with a certain RPM range in mind. And it makes me wonder if is dead time something that we could change as a user? We could go, well, I'm going to mess with it and make my ESC less likely to desync or fry when I run 6S 2700 kV. So
back in BLE S days, yes, you could, because the dead time multiplier was part of the firmware hex file.
And it was open source, so you could just change it?
Well, you wouldn't even have to. You just flashed a different version of the firmware.
Okay.
You would choose what was it, like GH30? Mm-hmm. So the 30 was the dead time multiplier. So you could go to GH40 and, solve your problem if you were getting ESCs that were heating up due to too low dead time. Now,
interesting.
Really, going to 6S shouldn't cause a problem with dead time, because dead time should stay relatively the same regardless. But if the dead time is off already, going to 6S may exacerbate an existing problem to the point where something blows up.
Especially because, as you said earlier, there's a certain amount of variance in the components that's used, and you may just have gotten unlucky with a FET that's particularly slow to turn on or off.
Or a capacitor that's on the gate line that's out of spec. That's the big one, is these little SMD caps that they use in a lot of our low-end electronics manufacturing stuff they derate like crazy. I mean, the rating window on those things is just, it's kind of crazy. So,
well, we wouldn't want to pay two tenths of a cent instead of one. I mean, come on, let's not be crazy.
I think part of it is just the way they're made. The ceramic capacitors, the tolerances are not as tight as some of the other methodologies. But yeah, I mean, when you're making a lot of stuff, I guess the cost per unit matters more.
So we've talked about that their higher RPMs results in more sensitivity to mistiming, missing the zero crossing or the having shoot through, and also increases noise, electrical noise, which also makes it more difficult to detect the zero crossing. Is that the issue then? When you go to these high RPMs, it becomes more difficult to detect the zero crossing and know when to sort of drive the coils. Is that what it boils down to?
And I think, like I mentioned earlier, I think the torque constant of a higher kV motor also plays a role, because you're getting, it's costing more current to produce the torque, which is creating more ripple, current ripple.
Well, let's talk about that. Because one of the questions people have asked is, could I go 6S 2700 kV and then use a motor scale to scale it down? So I effectively have the same RPM at the prop as if I was like 4S 2300 kV. And I said, well, I've done that and it kind of works, but then why don't we all just let's just take it to the extreme. Why don't we use a 10,000 kV motor with a 20% throttle cap? Why not? Why not, Ryan?
Well, the torque constant is the answer to that question. Within the range of things that we're typically using on our mini quads, the torque constant it varies, but it's not nearly as wild as if you had like as you're saying, a 10,000 kV motor. So the torque constant again relates to how much current it costs to produce torque. So again, when you're flying at a fairly constant forward speed,
right,
the torque request isn't a whole lot. So the differential between efficiency at a normal constant forward speed is not dramatic. I mean, it's there. You're going to lose some efficiency going to a higher kV motor, but it's not dramatic. Like, a couple of percent maybe.
Okay.
But that's not really where it plays a big role. It's more when you're making rapid changes in throttle, when you're hitting those high angle of attack maneuvers where you're basically moving backwards and you're trying to fly the other direction. So when you're really putting a lot of torque strain on the motor, when there's rapid changes, that's when you're going to see the spikes in current. Again, you're not even ever going to see those even in your logs in your flight controller, because we're not logging at a high enough rate to see.
When you say spikes, you mean spikes in the milliseconds or microseconds level.
1 to 2 millisecond range. Like when I'm testing on the bench, I'm recording. I don't know. It's like every 2 milliseconds I have a sample that's coming in. I can go down to 500 milliseconds or microseconds, half a millisecond. And I've done that and looked, and those spikes usually last for maybe just a single sample when I'm sampling at that rate. But those are, even on a normal setup, normal kV, normal voltage, you're looking at, they can be upwards of 160, 170 amps for on a single motor, right, for that tiny fraction of a second.
This is something about the ESC ratings that is often missed by people, especially when they're starting out, which is you have a 30 amp rated ESC. Well, that's continuous. Mm-hmm. You can burst for 10 seconds, maybe to 40, 45 amps. But what people really don't realize is that there are fractions of a second of spikes in the hundreds of amps for a very short period of time. And that's all sort of soaked up by the capacitance in the circuit and the battery. But those spikes can be enough to damage the ESC and damage the FETs, depending on various factors.
Really, in that regard, and this is going to be true with the high kV, high voltage setups even more than traditional setups, is that it's when that motor gets blocked, when it's trying to spin, that you're going to blow up. Because
that's when the torque demand goes right up, doesn't it? There you go.
You're hitting stall torque, and stall torque,
exactly.
It's going to fry everything.
That's fascinating. So I'm very familiar with KV, which is the voltage constant. Is that the right term? And I think most people are familiar with KV is the relationship between the supply voltage and the RPM that the motor tries to make. I'm less familiar with the torque constant, but that's a very interesting idea, and that really helps fill in that gap, which is that the higher KV motors, people say higher KV motors have less torque. That's not true. but higher kV motors need more current to make the same torque. And if you assume that current is not unlimited, then practically speaking, a higher kV motor may make less torque. And if it makes the same torque, it's going to be more likely to like fry something.
Yeah. So, and this is the reason why people think that a higher kV motor makes less torque is because they're operating by the wattage limits of the motor. So basically, a higher kV motor has a lower torque ceiling or within the wattage limit that
because you don't have unlimited power. If you had unlimited power, then you could run a 10,000 kV motor on a 20% throttle cap and you wouldn't notice the difference, but you'd be drawing a lot more power.
Right. So what happens is basically the high kV motor will burn itself out from the current cost of the torque production before the low kV motor. But people get confused because they hear that and they think that a lower kV motor is going to be able to spin up a prop faster than a high kV motor because they're thinking, oh, it's got more torque, but it doesn't have more instantaneous torque.
Interesting.
So it's not actually like if you look at the rate of change of RPMs,
right? Which you have
change the rate about the same, assuming all the other design characteristics are the same, like magnetic field strength, gap between the stator and the magnets, all of that stuff that impacts the actual instantaneous torque of the motor. Is if it's the same between motors, you're going to get very similar results in terms of how quickly the prop is changing RPMs if it's the same prop on both motors with the same requested throttle change.
Right, until you hit the power ceiling. And the power ceiling in a quadcopter, it seems to me like it would be defined, number one, as the point where you just draw so much current that you smoke your motor, or number two, the point where your battery just gives up and cries uncle.
Right, and in 90% of our cases, the current delivery capacity of the battery is the limiting factor.
Does that mean, but then, so we're getting a little bit off topic of 6S 2700 kV. Well, we want to come back to that, but we always range so many interesting places. Does that mean that people at 6S low kV, I mean, when we go to 6S low kV, we've got a lower kV and a higher voltage. So that should mean that the torque constant is lower and we get more torque for less watts. Is that correct?
Yes and no. I mean, you're also dropping the kV, so there are other things that go with that. But yes, in general, a higher kV or lower kV motor on higher voltage is going to have a lower torque constant, which means that those current demands are less, assuming the same characteristics. Now, that a little bit is misleading because oftentimes, even at lower kV, the combination of kV and voltage is still higher RPM.
That's true.
Than what a mid-kV 4-cell setup would be.
If you take like a 2450 kV 4S motor, the equivalent RPM, if you're at 6S, is like 1666, I think.
Yeah.
I'm not doing it's either 2450 or 2400, but most people don't run 1666 kV 6S. They run 1750 or 1800, and they're getting more RPM, so it doesn't quite even out. So what can we do then? We know like why high kV, high voltage causes problems. What can we do to not go 160 miles an hour and not desync? Sure.
So there's a couple of settings that you want to tune in your ESCs when you're dealing with high kV, high voltage to kind of give yourself the best chance of not having trouble. So I generally recommend a set of parameters. Some of them you can just set and forget. Some of them you're probably going to want to tune. And that's one of the reasons why I wanted to talk with you today is to walk through like how to tune that. Because This doesn't only apply to high kV, high voltage. High kV, high voltage exposes the need for it more than anything else. But this can also be a useful tool to tuning other setups as well. We don't often think about tuning our ESC settings when we're tuning.
That's true.
We tune the flight controller and a lot of people leave the ESCs on stock, or they have a set of parameters that they change every time.
Right. Like I usually go auto timing and 48K PWM, but I don't really like tune that. I just like, okay, it seems good.
Right. So what I usually will recommend to give the higher KV the best shot is turn DMAG to high, number one. Now, you may have some performance losses in some areas as a result of these changes, because basically what we're doing is we're trying to back off the instantaneous acceleration of the ESC to the point where we're not causing trouble. And we're reducing those current limits, reducing the noise factor. So the other one is fixing timing at between 23 and 25 degrees. Basically removing the parts of the code in the ESC, or not calling the parts of the code that are doing that auto timing calculation. So you're getting rid of some of the CPU overhead, and you're also, by increasing the timing, the higher the timing advance degree, the less likely you are to get a desync. The more ahead of time that you're firing on that, the less chance there is a desync. Again, you're going to lose a tiny bit of efficiency, but you're also gaining back a tiny bit of support as well.
I think if you're running 6S 2700 kV, efficiency is really not your priority.
Right.
Fair enough.
So now to compensate for that, so the DMAG high in combination with that setting, and then the one that you really can tune, and this is the one that's really the most interesting, I think, is the ramp up power. So in our BL Heli series, when we were talking about this, we talked about this briefly. But basically, I've done a bunch of testing on ramp up power, or startup power, as it was called previously in previous versions of BL Heli. So this has to do with the maximum rate that it allows the ESC to change the PWM duty cycle. So it's basically limiting how quickly it can jump duty cycle on the FETs. So that you can reduce that pretty dramatically before you start seeing any sort of noticeable change in how quickly the motor changes RPMs. Basically, what we're doing is we're reducing that current dump that happens into the coils in that moment between when the requested throttle change happens and when physically the motor starts spinning faster.
That's interesting, because the motor can only change speed so quickly because it is a physical object with mass and inertia. And so it reminds me of, like, if you have a really, like, an underpowered car and you just step on the throttle and the engine goes, whoa, and the car just doesn't go anywhere. And it slowly starts to pick up speed. And eventually it gets up to 60 miles an hour, but you've been just redlining the engine the whole time. As opposed to if you kind of like just baby it a little, it'll get there just as fast, but you won't stress it as much. Is that fair?
Right. So the goal is in tuning ramp up power is to reduce it to the point where you get the best reduction in that peak current in that 1 millisecond range without actually having any noticeable performance loss.
Right.
So what I'll usually do is back it off until I notice a difference, and then increase it slightly again until that difference is gone.
I think bidirectional D-shot probably is going to, because you have a thrust stand setup that most people don't have, but I think bidirectional D-shot may be a good tool to help with that, because it's giving us 1,000 times a second or something, whatever the D-shot rate is. It's giving us the instantaneous RPM of each of the motors. And it's a very useful tool if you're into black box logging to be able to look at the response time of the motors.
And you can use the toolbox and the response graphs there to do some of that as well. Basically back it off until you start seeing decreased response decreased response times, and then pull it back up again. But honestly, even there, unless you're noticing your noticeable difference in the tune or in the feel of the sticks, even if there is a slight difference in PID toolbox or in the RPMs, if you're not able to detect it as a pilot, it doesn't really matter.
Yeah,
so,
for sure.
I would say I don't even usually bother doing any of that. I just pull it back until I can feel a difference. But pull it back up until I can't feel it anymore.
What's the default value for this? What is it again? Ramp up power? Is it the parameter?
Yeah, 50% is the default value for ramp up power. And I usually start out by dropping it to 25 just right off the bat.
And you don't even notice a difference?
And I usually can't notice a difference at 25.
Okay. Interesting. Well, and especially if you're trying to do one of these really radical builds, like if you're falling out of the sky at 70% throttle, then maybe giving up a little bit of responsiveness is an acceptable trade-off.
That's
So it sounds like
so,
demag to high, demag compensation to high, timing, you said 20 to 23 degrees timing.
23 to 25 degrees on that.
Oh, sorry, 23 to 25 degrees timing. And ramp up power, reduce it, just start by knocking it down to 25%, and then maybe even go a little further than that.
Right. And basically, if you're having desync problems, just keep dropping it until the desync problems go away.
What about PWM frequency? So, some people have said they changed PWM. Do you think what kind of effect do you think that has?
So yeah, this is a really tricky one because PWM frequency has a ton of variation depending on the specific motor, the specific ESC, and how the RPMs relate to the commutation rate and the throttle, input, all of that stuff. Those all overlay on each other to kind of interact with how PWM rate works. So in some cases, you'll see dropping to 24 kilohertz actually solve some problems.
Yeah.
In some cases, you'll see the same problem solved by going to 48 kilohertz. It's
true.
One of those things where it could go either way. You just have to kind of test it and see. I was helping someone tune in a quad that they were having some low throttle vibrations on the other day, and this is the craziest thing. So they were having low throttle vibration, and we completely got rid of it. And they had dropped to 24 kilohertz. Everything was good, and then they crashed.
Oh no!
And after the crash, the quad wanted to just take off to the moon, and they couldn't do anything about it.
Wow!
So
That's
we
bad.
were playing with it, and we were like, "What on earth? That makes no sense." They went back to 48 kilohertz, and the problem went away, and everything was fine.
Well, that's crazy. I've been hearing people something about Betaflight 4.2 is bringing out low throttle instability,
So
and the devs swear
out this week.
Yeah, and they're making recommendations that people who are running 48K PWM go down to 24K because the lower PWM frequency gives slightly more torque and at low throttle specifically.
And this actually is what cued me in onto the solution on this. I had a bunch of quads that flew great back at like 4.0 and previous to 4.0. And then I have a bunch of them that fly really good on 4.1, 4.2, 4.0 with the RPM filter. But I had several where they just always had these low throttle or kind of low end. They would just start to move around, and I could never figure it out because they flew fine before.
Yeah.
So on these quads before, when I was tuning, I would get into this loop, and I'm sure you've experienced this in the past, where when you're tuning, you raise P, but you start getting some weird bounce back. So you raise D, and then you raise D. Yeah. You start chasing P and D. So I always had to run lower P than what I was necessarily happy with on those builds because I would get into that cycle of tuning that would just run away. So I could get them to fly good in like 3.5 on fairly low P gains. But then I was thinking about why would going to 24 kilohertz solve the problem for some builds, and I started talking with some other guys who are tuning, particularly guys who were tuning large quads like 6-inch, 7-inch, and who had gotten really good tunes without a lot of the shakes that are a problem on those builds. And like something just clicked in my head, and I started playing with it. So when RPM filter actually kicked in, it changed some things about how we tune because of the way the filtering was being.
Yeah.
We have a cleaner signal. We can change the way we tune. And when that happened, I never really went through a full retuning process on 4.2. I just kept slapping kind of my same numbers on there and never really changed it. So here's the thing, though. The RPM filter and all of this better filtering has really eliminated that issue with the P bounce back and chasing P and D. So I went back in and retuned everything and upped my P gains by like 50%.
Wow.
And all of those low throttle oscillations disappeared like that.
That's interesting. Well, it sounds like, if you increase the P gain, that will increase the response of the PID controller and get the motor out of that low torque, low RPM region faster, I suppose.
Yeah,
I don't know, though.
I think it's just giving it more control at that low end point, and it's responding more quickly. And, I'm kicking myself for not realizing this sooner because, I mean, you and I remember tuning back in the multi-lead days, right? And we used to call it dump trucking. Remember where you get, and it was because your gains were too low and you would just,
yeah.
And I hadn't had to deal with that in so long that like, I didn't make that connection in my brain, but basically what we were doing was dump trucking.
Interesting. Interesting. Well, so, that's really cool, Ryan. That's, there you go. That's the answer. Is that the answer?
Is running P gains up in this like mid 60s. And I've been helping people tune in some 7-inches that are running P gains up into the 70s.
Wow.
And all of those struggles we had with the large crop sizes causing all kinds of weird issues, I think were related to, number one, the frames being physically larger, which changes the relationship with the PIDs, the props being physically larger, so changing speeds slower. And like, you get into this mindset, though, I can't go too high because they produce more thrust, so I shouldn't need more P gains. But P gains are all on that initial acceleration.
Mm-hmm.
And that's where they really need that boost to be able to stabilize better.
That's interesting. That's interesting. Because the larger props will respond slower. So you need that higher P, even though that may be making more thrust overall, you may need that higher P gain to get that acceleration going. At the same time, we're talking about lowering the ramp up time to help reduce the demand for acceleration. But that's one's in the flight controller and one's in the ESC. So right. I guess they're not the same thing.
Well, and that's what I'm saying. If you start noticing bad characteristics on ramp up power, you've probably gone too far, because the goal is to pull back the current dump into the coils in the ESC without actually changing the rate that the ESC accelerates.
Right. You're not just sitting there screaming at the motor, when it can't accelerate any faster than it already is. You're just going to dial it back. Right. To match the capability of the motor to change
that
speed.
Has a big impact on noise production in the ESC. So backfed noise, power line noise.
Are you saying we could get cleaner video by lowering our ramp up power?
I haven't fully tested that theory, but in theory.
No, that makes sense, because when the motor changes speed, if the ESC demands more torque than the motor can possibly respond with, then you'll get these big current spikes, and that makes video noise. That's interesting.
And, even just the inductive nature of that current being sucked suddenly through all of the lines in the system, and then you've got voltage fluctuations as a result of the current draw shifting rapidly. So you're seeing both voltage and current, fluctuations creating EMI in the system. So, I mean, in general, it's if we can reduce the initial spikes of current in that, we're cleaning up the entire thing. And I think this even has a bigger impact in 4-in-1 ESCs, where you have all 4 ESCs in a single PCB. That's going to have a bigger impact on EMI and things like that.
It makes me wonder, though, why do they ship it? If you're saying that you could probably lower it to 25% on most builds without ever noticing a difference, why do they ship it at 50?
Well, you have to think, I mean, yes, a lot of these ESCs are for mini quads, but I mean, we're a tiny section of the hobby that uses ESCs, so I don't know that. I think for some other applications, it might be different. I don't work on
what
that.
kind of, could you speculate what kind of application would need a higher ramp up time? Maybe smaller motors that are able to respond quicker?
That's the real kicker, would be like 1507 and lower.
Gotcha.
And some of the really tiny stuff, you may actually, I haven't played with it. That's a little out of my realm of testing. But there may be reasons to go the other way on some of these really small ones.
Right. I guess you're trying to find a balance between the motor's ability to change speed and the ESC's demand that the motor change speed. If the ESC is just demanding more speed than more change in speed than the motor can provide, then you get current spikes. If the ESC is not driving the motor aggressively enough, you'll get less responsiveness. So theoretically, people with smaller motors, if they were to increase the ramp up time, maybe they could get a little more responsiveness with no real downside.
Yeah, it's one of those tricky things, because I know people have been disabling braking on some of the really small setups, in order to solve some of that current dump issue. So it might be interesting to play with some of those settings in those small environments and and see how it changes things.
All right. Well, great. Now we have the secret. Any other settings that you can think of that people should be noticing? Sounds like the big one. I think we knew the guy who built my quad, Phantom FPV, he goes by. He did the DMAG and he did the timing, but he didn't mention, I don't remember him mentioning changing ramp up power. Anything else that we should be thinking about?
A lot of people mess with because I think a lot of people don't really know what it does. Yeah, it actually, I think it's one that's probably one of the more important ones to tune. And you can play with the mixing of some of these as far as you might be able to reduce ramp up power, but then turn DMAG back to low. Just kind of play with some of the combinations to see where that sweet spot is and where you're doing the most to eliminate DMAG situations without causing any problems in terms of the ESC's response time.
Yeah, cool. I really appreciate you reaching out to me with this because when people ask questions, I like to be able to help and I like to be able to answer them. And I really have had nothing. I'm like, I don't know. We're so far beyond the pale with these quads. I have no idea what to recommend. So it's great that I now have one more thing to recommend, which is adjust the ramp up time.
I would say that I have not seen very many cases where ramp up power doesn't solve the desync issue. But There's one thing, one word of caution with this is that when we're pushing the limit on setups like this, sometimes it will expose bad hardware. And what we can end up doing is putting a Band-Aid over bad hardware. So
how do you Yeah, go ahead.
It may make it work, but you may be covering up bad hardware.
I'm glad you said that because I meant to ask you this earlier, but then we just got distracted. How can people recognize a good ESC that is more likely to work other than just looking at, we know that there are certain ESCs Phantom used the T-Motor F55A. I've heard people using the Hobby Wing and say there are good things about it, the Hobby Wing 60 amp. How can people... Is there some spec or characteristic people can look for that will say that an ESC might be more likely to tolerate this kind of treatment?
I mean, yes, but without getting into a lot of looking up the specific FETs that are on it and looking at the data sheets and looking at, RDS on times and things like that. But even there, you would have to know more about how the circuit was designed around those FETs to really be able to predict it well. But if you just look at the FETs and look at the actual data sheet on the FET, it's going to tell you a lot about kind of the limits of what that ESC is capable of producing. What kind
of specs for people who are dedicated enough to do that? What kind of specs would you be looking at on the data sheet?
So you want to look at the thermal dissipation capacity of the package. It'll tell you what the thermal dissipation limits are, and also you want to look at both the sustained current ratings and the peak current ratings. And they actually have a pulsed current rating that is really a good thing to look at too, that can tell you what those kind of instantaneous peaks are. Usually they're in the 200 amp range, and that's really kind of what you want to look for.
Okay.
But you can end up getting, out kind of down a rabbit hole going into all of that.
Well, the first thing you would need to do is just find the actual FET. And you would need to find a photo maybe of the ESC and look and see if you can see the label, or you buy it and they're stamped on there. But
and the RDS on time, as far as the time that it takes the gate to turn on and activate the FET, the lower that time, the better. But there's even that is subject to some interpretation because a lot of that depends on the rest of the circuit that's in line with the with the gate line.
Right.
So,
right.
And that's where, you get into some really interesting stuff when you start diving down these data sheets. Because if you start looking at it on paper, those metal FETs that they're using on some of these high-end ESCs, they actually don't look very good on paper in terms of, they have slower RDS on times. And there's some things that make them maybe not the best for what we would think of in our normal mini quad applications, but they appear to do okay in practicality. So.
Yeah, I've heard some criticism of some of those FETs saying they have like a higher resistance and they're going to soak more heat. That which some people have made the argument, and I don't know if it's true, that in certain in high current applications, the fact that they're metal so they can dissipate heat easier is offset by their increased resistance. And it sounds like it is, in fact, a pretty deep rabbit hole.
Yeah.
All right. Well, Ryan,
let me go back and answer that one question.
Yeah, go ahead.
Because I think the one thing that is worth looking at when it comes to an ESC is getting involved in the community and asking what has worked for other people. Because that's going to tell you things that a data sheet can't. I mean, obviously, you should take that with a grain of salt because some people have only ever tried that one ESC and they think it's working fine for them. And,
I hear people say Racer Star ESCs are so good. I've never had one fail, and I'm like, eh. It reminds me of the game. It's not you just pull a card out of a deck. You say Ace of Spades. Is that your card? No. Well, if you do that 52 times, if you just do that all day, eventually you'll get one right. And so somewhere out there's a person who's bought 20 Racer Star ESCs and not a single one has failed. Just statistically. Doesn't necessarily mean the Racer Star is the best ESC.
Right. And that's why it's important, when you're looking at qualitative analysis, you want to get a broad range of feedback from a broad range of environments. So like asking a lot of different people and getting information from a lot of sources, you can start to put together kind of a qualitative picture of which ESCs stand out above the others in terms of just general community feedback.
Yeah. Bear in mind also that there's more to manufacturing than the data sheet. You can have the best specs in the world, but if you have poor quality control, you're going to make junk. And that's where there are many good ESCs out there, but I always have my ear to the ground for the ones that seem to really excel. And the two that stand out to me are the T-Motor F55, the T-Motor F45, but it's not a 4-in-1, and the Hobbywing 60 amp. Those are ones that just people I know who beat the hell out of their gear just say that they are really, really solid pretty much across the board. Any ones you can think of that you feel like are probably pretty reliable?
Well, I fly probably 90% Acon stuff. So I really like the Acon 35 amp individuals. I tend to go individual route because I feel like I have more control over the noise floor and you can put a cap on each ESC. And just in general, I feel like I end up with a better quality tune with individuals rather than 4-in-1s.
Interesting.
I do. That being said, I have a couple of builds with the Acon 55 amp and the Acon 35 amp 4-in-1s that I've been able to tune in pretty well and get dialed in. So those are kind of my go-tos. But and I actually, I have not heard many of those failing either. So just in the community in general at large.
Yeah.
But there are other, these days, I think, there's a lot of really good stuff on the market, and we're in a time period where a lot of it is pretty decent. I mean, you can get a pretty broad range, especially when it comes to motors these days. I mean,
motors are pretty solid. You can get some pretty good motors at a pretty decent price. All right, Ryan. Well, thank you very much for just randomly saying, "Hey, I want to talk to you." Please do it anytime. I have so much fun when we talk, and I always learn stuff. So now I'm gonna be playing with ramp up power on my quads and seeing what I can do with them.
Yeah, I'll be curious to hear what you come up with.
Okay, awesome. Ryan's website is miniquadtestbench.com, where you do the most in-depth motor testing of anybody I know. Anything else that you've got going on that you want to plug? You have a frame, don't you? Do you actually sell that, or you just make it for yourself in your basement?
Well, I've gotten into frame design a lot. I'm doing a lot of contract work for some of the major FPV companies out there, doing a lot of contract design, that kind of stuff. But it's fun. I enjoy the design aspect. That's probably where I'm spending most of my time these days is doing product design and development. So,
okay, all right, man. Well, thank you very much. Happy flying, everybody. What are you still doing here? The video's over. Do you watch all the videos all the way to the end? Wow, you are a super fan. Thank you. That actually helps the channel a lot. when you watch the videos all the way to the end. YouTube loves that. You know what else YouTube loves? When you subscribe. Or when you join my Patreon for as little as $2 a month or more if you feel like I've earned. Actually, YouTube doesn't like you to join my Patreon. They don't get a cut of that.